Welcome back, chemists. In this last lesson for our first unit, we're going to continue to talk about techniques that we use to figure out what the structure of a chemical compound looks like. On your screen is a sample supporting information paragraph. This is what you do if you ever make a molecule in the lab, especially for the first time, and you have to report on its structure. You detail not only the experiments that were involved to make it, but all the analytical information that prove its structure or that really suggest what the structure is. At the very top on the right shows chemical representations for the reaction. This is an ester, I'll say, that's been reacted. Actually, the aldehyde group at the very top turns into what's called a hydrazone. This is actually a reaction I did many years ago, so this is from one of my old pieces of research when I was in graduate school. And the bottom line that I think we keep reiterating is that what you actually make in front of you physically looks nothing like the picture. When I made this, it was just a solid, and I certainly didn't have a big pile of powder like that one, but it was just a solid of some color, and it looks nothing like the picture. That's our representation of it. So how do we decipher what this thing looks like? Well, we can do things like take the melting point and make sense of what that is compared to other similar molecular compounds. We can take an IR and detect what kinds of bonds are present in that molecule. We talked about that in the previous lesson. Or we can take a mass spectrum. HRMS in the lower right here stands for high resolution mass spectrometry. So we found a mass spec, and it showed a molecular mass of 630, which is exactly what it should be based on the molecule that we were trying to make. We were also able to decipher it from what's called a crystal structure. We had another research group take a crystal structure of this, and that looks at its diffraction properties. This happened to be a crystalline substance, so that gives you a lot of useful information. It's almost like having a photograph of the molecule, so we were very lucky, but that's not always the case when you're making a new molecule. So in addition to that, we took what's called an Nmr Spectrum. That stands for nuclear magnetic resonance. And that's the last thing we're going to talk about in this lesson today. Very, very introductory. How do we interpret an Nmr spectrum of a molecule? So on your notes, there's a couple of paragraphs that talk about this. Nuclear magnetic resonance spectroscopy is used for detecting specific atoms. For example, hydrogen atoms in a molecule. Hydrogen is the most common one we look at for organic compounds because it's everywhere in organic compounds. Even though organic chemistry is the chemistry of carbon, usually most organic compounds have more hydrogens in them, and they're different enough that we can decipher how they are arranged based on an Nmr spectrum that looks at hydrogen atoms. But you can actually detect a variety of different nuclei in addition to hydrogen atoms. Due to symmetry, many hydrogen atoms have identical chemical environments, and they show up as the same signal, but different chemical environments will cause hydrogen atoms, different atoms, to show up at different positions. So we can differentiate between a hydrogen atom that's attached to, let's say, an aldehyde group, like the thing we're testing for in a Tollens test, versus a hydrogen that's on what's called an alkene, a carbon-carbon double bond. Even though they're both hydrogen, they're in a different chemical environment, and it doesn't take much to make the chemical environment different. So quite often, very complex molecules have very confusing looking Nmr spectra, and it can be quite challenging to decipher what all the different signals mean. We're just going to look at some simple ones today just to introduce the concept. Now there's a very useful feature of proton NMR, or hydrogen NMR, which is called spin-spin coupling. And this has to do with what are called neighboring hydrogen atoms. A neighboring hydrogen atom is simply a hydrogen atom that's in a different environment, and it's attached to a carbon that's adjacent to whatever carbon atom that I'm attached to. If I'm the hydrogen atom in question, and I'm attached to a carbon, and there's an adjacent carbon atom, and whatever hydrogen atoms are on that carbon are considered neighboring. They're close enough that their magnetic field affects mine, or the one I feel from the instrument, and I see what's called a splitting pattern. The useful thing about this is that you get spin-spin coupling, which results in a signal that shows how many neighboring hydrogen atoms I have, so we can quantify that. The number of peaks that a signal is split into is equal to the number of neighboring hydrogen atoms plus 1. I'm not going to go into why that is. You learn about that when you learn organic chemistry and study this in more detail, but I'll just show this graph in front of you. This is courtesy of the Compound Interest website, and it shows a nice illustration of the different signal patterns. Here is a singlet, which is when you have one hydrogen atom or some number of hydrogen atoms that have 0 neighboring hydrogen atoms. But if I have just one neighboring hydrogen atom, the signal is split into what's called a doublet. If I have 4 adjacent neighboring hydrogen atoms, the signal that's representative of me would be split into 5. It's always one more than the number of neighboring hydrogen atoms that we have. So let's look at a couple of spectra and just interpret them, and then we'll see if we can match a few unknown spectra with a set of molecules. So here are the spectra for the ethanol molecule, which is actually shown in the upper right, and the isopropanol molecule, which is not shown. So we're going to interpret the ethanol molecule and then figure out what isopropanol looks like based on its spectrum. So if I look at ethanol, it has a total of 6 hydrogen atoms, but some of them are in the same environment by symmetry. The 3 all the way to the left are in the same exact environment. They're all on the same carbon atom, and they're all experiencing the same chemical environment from what's directly attached. The 2 right in the middle are also in the same chemical environment, but slightly different than the other 3. That's because they're closer to the oxygen than the 3 on the left. And then there's the 1 hydrogen off to the right attached to the oxygen. So I have 6 hydrogens, but I only have 3 different types of chemical environments that show up in my NMR, and you can see there are in fact 3 signals in the Nmr spectrum, so that's what that shows. We can also integrate the spectrum and figure out how many hydrogens are giving rise to each of those signals. Remember, if you're in math class, an integration is a calculation of the area underneath a curve, and that's actually what these signals are. These are not linear peaks, they're actually 2-dimensional signals with a small amount of area underneath. It's difficult to tell because they're so narrow, but there is an area which can be integrated by the instrument itself. So we get a ratio in this case of 1 for this one on the left, to 2, the one in the middle, to 3 all the way to the right. So I have a signal that's due to 1 hydrogen, I have another signal that's due to 2, and then I have another signal that's due to 3, and that's why it says 1H, 2H, and 3H left to right. And lastly, the splitting shows us how many neighboring hydrogens we have. So off to the left, that singlet, that means I have 0 neighboring hydrogens. The 1H means I'm worth 1, but it means there's no one on an adjacent carbon next to me. Now, the next one, the quartet, that means I have 3 neighbors. Remember, it's always n plus 1. How many neighbors plus 1 gives the splitting pattern. So a quartet means you have 3 nearby hydrogen atoms. And then the last signal, the triplet means I have 2 neighboring hydrogen atoms. And right away I notice something. The 3 hydrogens that are next to 2 others makes me look more closely at the 2 hydrogens that are next to 3 others. So this is what this little graphic off to the right is attempting to show, that neighboring hydrogens will always see each other. So if this group is splitting that group is also splitting this group. It always goes in both directions. So this triplet is because these 3 are seeing these 2, and this quartet is because these 2 are seeing those 3. So we know that the signal all the way to the right is a CH3 group. It's worth 3 hydrogens, and it's attached to a carbon which is attached to some other carbon with 2 others, and that's the 2 in the middle. We already know what they are because there's the structure in the right, but we're deciphering this. What about this last signal? Well, that must be the OH signal, and you might be looking at that and going, how come there's no splitting involved? Well, because the hydrogen is on an oxygen, we hardly ever see splitting. Usually, not always, but usually splitting patterns are only observed for hydrogens attached to carbon atoms, particularly as is indicated in this simulated NMR. This is actually just a simulated one from ChemDraw, but it does a perfectly good job at teaching us how to interpret them. What about the spectrum down below? Well, there's the spectrum of ethanol first, so there's just the same molecule redrawn. Now let's see if we can interpret the one below and figure out what this molecule looks like. So left to right, I have a signal that's got 1 hydrogen. It looks like a singlet, so it has no neighbors. Then there's a septet right in the middle, and then there's a doublet all the way to the right. So the septet means I have 6 neighbors. The doublet means I have 1 neighbor. It's always 1 more than the number. What about this 6 hydrogens? You can't have 6 hydrogens on 1 carbon, but you can have 2 CH3 groups. And those 2 CH3 groups, if they're all in the same environment, would give rise to 1 signal. They'd be worth 6 as a total. And then if they have 1 neighbor, that means they're both attached to a carbon with only 1 other. And that must be this other signal over here. We've got a 1 hydrogen signal with 6 neighbors. So again, these 2 signals I can sort of pair together and figure out that they're all connected to one another. So this is a carbon with only 1 hydrogen on it, because it's only integrating for 1, and it has a total of 6 neighbors. What's off to the left here? Well, if I look at my molecular formula, which maybe I was able to get from mass spectrometry, I know that I've already got 7 of my 8 hydrogens, so there's 1 left. And there's an oxygen, so that must be an OH signal. And there's only one way for those to go together, and it looks like that. And that is indeed the isopropanol molecule, and that's its NMR. Now you can imagine combining this with things like mass spec that would confirm or highly suggest the molecular formula by giving us a molar mass. And I would certainly take an IR of this to show that I see that OH stretch, that broad oxygen-hydrogen bond that you see up in the 3500s of an IR spectrum. There's a couple of matching problems on the back. Let's just go through those to see if we can understand this. So here are 4 molecules that are somewhat food-related, just to bring it full circle back to our discussions of foods. Citric acid and piperine are found in citrus fruits and in peppers. 2-bromopropane is just a random organic molecule that's not food-related, and acetone is more of a hygiene product. That's a nail polish remover. So which spectrum goes with which molecule if this is a matching game? Well, the first one has a 1 hydrogen signal that's split by 6 others, and a 6 hydrogen signal that looks like a doublet, but be careful, those could also be 2 separate singlets. And they must be. In fact, that's identical to what we saw just a moment ago with the 2 CH3 groups. And that is enough to actually figure out which molecule this is. You could just add it up and say there's 7 hydrogens. There's only one molecule up there that even has 7 hydrogens, but it makes sense because I could have that 1 hydrogen signal with those 6 hydrogens. This is the 2-bromopropane molecule just by process of elimination. What about the one right next to it? This has nothing other than a singlet. Notice there's no integration written because there's nothing to compare this to. The integration is just a relative ratio of hydrogens. It's not absolute. But if there's only one single signal, then there's only one type of hydrogen. So they're all in the same type of environment. And of the remaining 3, this must be the acetone molecule because all 6 of those hydrogens are attached to a carbon that's attached to the ketone in the middle, the carbon-oxygen double bond. So this must be the acetone molecule. Below that, I have a little bit more complicated of a spectrum. It's all singlets, 4 different signals in a 4-to-1 to 2-to-1 ratio, right to left. Off to the left are these signals that are quite far in the spectrum on the x-axis. These look like carboxylic acid signals. If I go all the way back to the beginning of today's lesson and look at the location of where the signals are showing up, notice we're barely even using that aspect, but it's still true that where they show up is a little indicative of what type of environment they're in. And if I look above the remaining 2 molecules, this must be the citric acid molecule. There's an OH group that must be off of the middle carbon there, and 2 CH2 groups, what are called methylenes, that are in the same environment by symmetry. There's one in the molecule, and there's the other, and they have no neighbors, so they show up as one signal. So by process of elimination, the very last one, which I'm not going to decipher completely, it must be the piperine molecule. You can look at it more closely and maybe try to identify which signals correspond to which hydrogen atoms in the actual structure. That's a fun exercise, but we're not going to go that detailed in this level of the class. This is just meant to introduce you to how Nmr spectroscopy works. Okay, so since we've reached the end of our unit, let's summarize a couple of things we've talked about in this first unit, all about matter. Elements are what make up the periodic table, and they make up everything we talk about in chemistry. That's our alphabet when we speak this language. Speaking of language, we need to be able to know how to name compounds. We went through binary ionics, polyatomic, transition-containing compounds, covalent compounds, simple covalent compounds, and even acids. Then we started to talk about mixtures and how we can separate them using things like chromatography, crystallization, distillation. And once you separate them, how can you tell what you have? You can run chemical tests like the starch test, the tolerance test, or physical tests like melting point and boiling point. And then more recently, we've been talking about analytical techniques. Things like mass spectrometry tell us what's the molar mass of that compound. IR spectroscopy tells us what bonds are present. And today, Nmr spectroscopy tells us what atoms are there, and more importantly, where are they arranged and what's near them, what type of environment are they in. And most of the time, none of these techniques by themselves is enough to really conclude what a molecule looks like, particularly if the molecule has never been made before. But you can imagine combining all these techniques together, and that's what chemists do when they're deciphering a molecule. Okay, that wraps up our first unit. Good luck on your first assessments, and thanks for watching.